Hi, my name is Kruthik Alapati, and this is my physics lab on oscillation. So the objective of this lab was to create a model predicting the motion of an object attached to a spring using a computational model and comparing it to an observation of the same motion in real life. So what are some important concepts to this? Well, Newton's second law, because we're going to be discussing the forces that are acting on the object and how this causes the momentum of the object to change. So you can see here F equals mass times acceleration, and then in this case the net forces on the object were the force of gravity and the force of the spring. And the change in energy should equal zero, as those are the only two forces acting on the object, which means there's no external work being done on the object. So here are some equations that we'll use. We have the equation for kinetic energy, which is 1/2 mv squared. We have the equation for gravitational potential energy near the surface, which is mgh, or mg in this case mgy. And we have the gravitational force, which is F equals mg, which is the mass of the ball times the gravitational acceleration. We have the force of the spring equals the spring constant times s, and you can see s is the current length of the spring minus, or sorry, the magnitude of the spring minus the relaxed length of the spring. And you have the spring potential energy here as 1/2 ks squared, and you have the rearranged formula for k from the period. K equals 4 pi squared times mass over the period squared. And we'll use these and calculate our values for our glow script model on the next slide. So here are the calculations we did for our glow script model. Our period was done by taking the time for 3 complete periods and then averaging it out. So we have 1.646 seconds. The spring constant was found using the formula that I showed you on the last slide. So the spring constant is 5.8577, and the relaxed length of the spring was found by setting the magnitude of the gravitational force equal to the magnitude of the spring force, and then rearranging it to find s, and then rearranging s to find the relaxed length of the spring, which was 0.02745 meters. So here's the tracker model I had for the motion of the object connected to a spring. And here you can see that the motion of the object was tracked using tracker, and the oscillating x and y position are shown to the right, as well as the data that was inputted into Excel. And then this data was put in the glow script model as well to be compared to the computational model, which I'll show you the code for in the next slide. So here's a glow script code I had for my model. You can see the mass of the ball, 0.402 kilograms, is right here. The initial position that we got from the tracker model is right here, and the initial velocity is 0. We have a small change in time interval, and time starts at 0. The gravitational acceleration is 9.8 meters per second squared. The spring constant that we solved for earlier is here, and the relaxed length of the spring that we solved for earlier is also here. And then we have the spring length, which is done by doing the position of the ball minus the position of the spring. The direction of the spring, which is done by doing the position of the spring vector over the magnitude of the spring vector. And then we have s equals the magnitude of the spring vector minus the relaxed length of the spring. And then we have our kinetic energy formula right here, our potential energy formula right here, our spring potential energy formula right here, and the total energy, which is the kinetic energy plus potential energy plus spring potential energy right there. So on the right, we have our while loop to do all the updates. So we have our initial energies right here, and then we have our gravitational force, and the vector for that is just 0 because there's no force in the x direction, and then negative mg in the y direction and the 0 in the z direction. And for the spring force, we have negative ks in the direction of the spring, which is L hat, and the net force is just the same as before, gravitational force plus spring force. So for the velocity of the ball, we have the velocity update formula from the momentum update formula right here, which is the velocity of the ball is updated by the net force divided by the mass of the ball times the time interval. And then you have the position of the ball update formula right here, which is the position of the ball plus the velocity of the ball times the time interval, or change in time, sorry. So then you have the spring update, and here we're just going to use the formulas from before. The length is updated by the position of the ball minus the position of the spring, which is the origin. The direction of the spring stays the same with the position over the magnitude of the position vector of the spring. And then you have s equals the magnitude of the spring vector minus the relaxed length. And then you have the change in energies, and so you have the final kinetic energy minus the initial kinetic energy. You have potential energy minus initial potential energy, and then you have the spring potential energy minus the initial spring potential energy, and then you have the change in energy being the energy minus the initial energy. So here's the glow script model, and you can see the red is the observed and the blue is the glow script. You can see a discrepancy here, which is likely due to drag not being accounted for, and you can see the energy graph right here on the bottom. For future studies, I would account for drag in the computational model to make a more accurate model, and this would probably get rid of that discrepancy that you saw in the last slide. So is the energy principle satisfied? Well, according to my model, it seemed like it wasn't satisfied because the energy seemed like it was changing. This shouldn't happen, and the energy should stay at 0. This could be due to the model being bad or poor computational power. So from tracker, I saw that the X period was 1.646 and the Y period was 1.488. And this means that it's moving faster in the Y oscillation than in the X oscillation.